Welcome to the interpretation of faults and fractures in OpenDetect. I will start the presentation with introduction, and I will show you how we interpret faults in 2D and 3D using the free platform, and also how we compute some attributes that would help users to highlight those structure features in their seismic data. The second part of the presentation, which is basically will be focusing on the commercial tools that are designed specifically for faults and fractures. So basically, as you know, OpenDetect consists of two parts: the free or the open source, which is basically a seismic interpretation platform or system that users can utilize to do 2D and 3D seismic data interpretation that includes, but not limited to, fault picking, horizon picking, etc. On top of that, we have OpenTect Pro, and that's the closest source part of OpenDetect. Basically, it has extra functionality for professionals, and OpenDetect Pro itself can be extended further for with the commercial plugins, which are designed for specific and unique seismic interpretation workflows. Users can pick faults in OpenDetect either 2D or 3D in two ways. First, by picking a fault. It can be a major fault, can be a minor fault, and you do this in number of inlines or cross lines, and eventually you generate 3D fault plane. But also you can use the fault sticks, which allows users to interpret more than one fault in one section. The difference between the two is that, as I said, the fault stick, which is basically a segment that consists of two nodes or more, that allows users to do or pick a number of faults in one section. Here's an example from New Zealand. This zone is, as you can see, it's heavily faulted. So in this case, we use fault sticks to interpret those faults. If you are dealing with the faults in 3D volume, so basically the first thing you do when you interpret faults is by seeing them in seismic data, and then you start picking the major ones. And as you move on, as you continue interpreting, you create a 3D plane, as you can see here. Optionally, you can add seismic attributes or seismic data on the fault, as you can see here in this image below. We also offer some attributes that also can help users to identify and delineate structure features, such as the similarity attribute. Similarity is a form of coherency, which expresses how two or more trace segments look alike. Similarity of 1 means that trace segments are identical in a waveform and amplitude. Similarity of 0, however, means that those traces are dissimilar. In OpenDetect, we have a little bit a different approach, because we basically we calculate the dip. We try to find the direction of the best matches at every location, and that's basically the dip field. So by using the dip, we calculate the best similarity between the adjacent traces, which basically result in a better definition of faults or any other geological features. So what you see here is an example also again from the New Zealand dataset, and on the left side that's a seismic section, on the right side that's the non-steered similarity attribute results. As you notice here, the white features here are supposed to be the faults. I can see that this non-steered similarity did a pretty good job here in this section, but if you look at the rest of the image here, there's a lot of whitening here. So yeah, we can argue about this. Is this can we do better job than that? So I want you to remember this slide carefully because we're going to come back to it. Now I'm going to jump to the second part, which I'm going to focus on the commercial tools that we design for faults and fractures. So basically, the main plugin we have is, of course, the faults and fractures. And the way we design it, we put all the attributes, all the tools, all the filters that related to faults and fractures under one umbrella. So we want to make the life easy for our geoscience community. And also recently we developed the machine learning, and we have one of the most powerful algorithm that can predict faults in 3D seismic volumes. Both plugins are standalone. That means you don't need any other plugins for them to work. Of course, you need a Pro and to make these plugins work. However, we highly recommend users, if they are working on data and they want to interpret their faults and fractures, etc., to get the dip steering, because we found out from our extensive experience working on data from almost everywhere on this globe, that dip steering make a lot of difference. And I'm going to show you examples and how this attribute, or how this plugin provide better results. So we will start with the fault and fracture plugin. So the main features or the main highlights in this plugin is the thin fault likelihood. It's a power of semblance. It's an attribute that produces sharp images of faults. If you are working in a fracture basement reservoir, then the BFL, or the basement fracture attribute, is designed to image those steep dipping reflectors. If you work in an unconventional data set, then fracture density and proximity also, they are good attributes. Data conditioning is also, it's a very crucial step for the structural interpretation. So the EBS, or the edge preserving filter or smoother, also is a very important element here in this plugin. And of course, we do support the automatic extraction of fault planes. If you combine this plugin with the dip steering, then you can create a dip steering filter. It's an enhanced version of your raw data. You can also by computing the dip and azimuth, you can directly compute other attributes such curvature or similarity, and etc. The fault and fracture interface is, as you can see here, this is the fault block, and yeah, we support 3D and 2D, and as you can see here, we have a number of categories. I will try to cover as much as I can in this webinar. The first attribute I will talk about is the fault likelihood. So basically, that's nth version of the TFL. We use it as an input to either create the TFL, or also we use it as an input to extract the fault planes. So what you need to use here as an input is your seismic input. You can use the raw data, but as I mentioned before, it's highly recommended to enhance your seismic. You need to apply some of our filters, and yeah, those filters require the dip steering. So that would be the output of the fault likelihood. It's a probability volume, and then you apply a thinning algorithm to get a sharp edge of these faults. When it comes to fault extraction, so you can use this one, but what we recommend is to use this input. I'll show you that later on. The attributes, so once you create the depth field, you can use those directly to compute the curvature, which is an amazing attribute that highlights and delineate the structure elements in the seismic data, as you can see here, which is basically a Barahaka fault system. Yeah, if you are working in an unconventional data set, then we do have two attributes that are derived directly from the thin fault likelihood. The fracture density attribute and the fracture proximity attribute. The fracture density, basically, it tells you where you have high dense fracture zones in your data, which is basically might be the sweet spot and the thing that you're looking for. The fracture proximity, on the other hand, it tells you in distance how far a certain fracture from other point, for example, from your well location. So again, identify potential drilling hazards. The similarity attribute, I already talked about it and what it is. So again, it is known for its capability in capturing the faults and fractures or any other structural elements in the seismic data. In this case, so again, I use this is a similarity that's steered. We use the dip field here in order to calculate the best similarity between the trace segments. So you remember that's the image or that's the slide I ask you to remember, because we're gonna come back to it. So this is a comparison between the non-steered similarity and the steered similarity. The similarity that we did not use the dip field to compute the coherency, and the one that we used it, and you can tell the difference. You can see how we improve the definition of faults between these two images. It's just amazing. And also, again, this is also a comparison between the similarity, but in a horizon, or a z-slice here, in a horizon actually. Yeah, so you can see the non-steered similarity on the left side and the steered similarity on the right side. So you can see the clarity and the amount of noise that was reduced by just using the steering volume as an input, or as a guide to compute the similarity. The other tools that we have in this plugin is the filtration capability, or the filters. I'm not going to talk about this because my colleague Dr. Paul Dichroet covered this in his webinar last November. So if you want to know more about the filters and the difference between them, please look at this webinar on our website. Other tool also very important is the skeletonization. This is a tool that allows you to fine-tune the fault probability volume. This is suitable specifically for the probability volume that we produce using the machine learning. So this is basically a thinning algorithm. Yeah, so this is the interesting part about this plugin is the fault planes. Everyone is interested to extract nice and smooth fault planes. So it's a very automatic way. So once you create the fault likelihood, this is what we recommend. We get the best results using the fault likelihood, but still you can use the TFL as well as an input to extract fault planes. So this is the interface of the fault scan processing setting. So the fault planes, we call them fault scans at the moment before we extract them. You have a few parameters to fill here. The most important thing is the minimum scan size. So if you are interested in the small size faults, then you may decrease the skin size. If you want to discard the small ones, you want only to worry about the major ones, so you may want to increase the minimum skin size. Again, so this is the fault scan QC. So the main highlight in this window is the steer unit kind of thing here that allows you the where are or the direction of your faults The green squares here, or the dot you see, this is the one that I selected for extraction. So if you select all of them would be turned into green. But also we do have, this is very important here, we have the filtration criteria that allows you to, again, to discard any artifacts, any faults that you don't think they're real. So using those green bars here, this allows you to filter based on a skin size, based on a strike, based on an average dip. And eventually you can see the number of skins that in range. This is what you want to extract, the numbers, like the total, as you can see, is 2000 something, but what you want to extract is might be less than that based on the filtration criteria you used. And once you're okay with the criteria you set, then you just hit on the extract button, and you will extract your fault set. All these faults, they will be stored in one file, or what we call a fault set. As you can see, they are smooth and nice. However, you can then individually, or you can extract these faults individually. So you can see here we have so many tools available for you to deal with these faults. And also, if you want to do more analysis for your faults, understand where are they in terms of dips and strike. Yeah, you can use. Here you can use also the rows diagram for more fault analysis. You can do that based on the strike only, as you can see here, but also you can use as a combination between the dip and a strike. If you are interpreting horizon in a heavily faulted zones, and you want to improve the relationship between the fault and the horizon, then we have the trimming features also for you, where you can trim your horizon against one fault and a few faults, or a whole set of faults, just like I have here as an example. And after the trimming, that's what you see here, and you can decide how much you want to trim per trace. These white batches are these faults. The last thing I want to talk about is the machine learning plugin, and specifically the Unet fault predictor. I'm not going to talk a lot about this machine learning, because my colleagues covered in the previous webinars. Well, I'll just want to highlight the tools that allows users to image faults. So you can use the transfer training, for example, to image faults. I understand that we are working at the moment to allow users to pick fault sticks interactively while they are extracting their examples and before doing the training. This is not available at the moment, but this is something we are working on, and it will be available soon. And of course, here's the Unet 3D fault predictor. It's a model trained on a simulated data, and will be applied on unseen real data. So basically, it is powerful, super fast tool, allows users to estimate and predict faults or fractures in their seismic data. The model, again, as I said, is trained on a synthetic or simulated kubelet of 128 by 128 by 28. The good thing is that the interpreter does not need to train or extract any examples, because this is a pre-trained model shipped with the plugins. So all you need to do is just apply it as is on a data that this model never seen before, and you will be outputting faults and probability volume, of course. And this is the example here. So basically, you just highlight it from the control center, and you click on go. You input your seismic data. It could be the raw seismic data, it could be the enhanced one. It's up to you. And then you hit run, and the output very nicely well-defined faults. Now, if you want to use this to extract fault planes, that's also possible. So we recently added a new tool that allows you to combine the dip and strike component from the TFL with this fault probability, and then you can use it to extract fault planes. With this, I conclude this webinar, and yeah, you can, as you can see, that OpenDetect offers wide range of tools that help users to interpret faults either in 2D lines or 2D seismic cubes. OpenDetect also offers one of the most sophisticated attributes in the market that combine attributes, filters, fault plane extraction, again under one umbrella, and that's the fault sample plugin. As I said, the plugin does not need any other plugin to work. However, it's a standalone plugin. However, we highly recommend the combination with the dip steering. As I showed you the differences when we talk about the similarity attribute. Of course, our machine learning unit fault predictor is a very powerful, great tool that helps users to predict seismic discontinuity. So it's a great in terms of powerfulness and also in terms of processing speed. By this, I conclude this webinar, and thank you so much for attending. And if you have any question, please go ahead.